Hi, in this video, I present our work exploiting virtual array diversity for accurate radar detection. Recently, there has been a significant amount of work on using millimeter wave radars for the perception of self-driving cars. However, obtaining semantic scene understanding from radar images is challenging because the angular resolution of radar is extremely low. In this work, we introduce Radatron Plus, a millimeter wave radar-based object detection system that leverages high-resolution cascaded MIMO radar to accurately detect precise bounding boxes of vehicles. The cascaded MIMO radar we use combines 12 transmitters and 16 receivers to emulate a large virtual antenna array with 192 elements. This provides us with 1.8 degree Atmos resolution, which is 10 times higher than single-chip radars. However, the quadratically improved angular resolution comes at a price, because MIMO radars require multiple transmissions from the time division multiplexed TX antennas to construct a high-resolution heat map, which leads to two unique challenges, especially in highly dynamic scenes like moving cars on the road. First, the Doppler phase shift across multiple transmissions can blur and distort the resulting heat maps. Second, the low frame rate also leads to loss of ambiguity in Doppler velocity estimation. To overcome these challenges and take full advantage of the high angular resolution of cascaded MIMO radar, Radatron Plus jointly leverages a variety of virtual array topologies in a hybrid radar signal processing and deep learning solution. Let's first look at the Doppler phase entanglement issue. The phase variation across antenna array due to the antenna spatial diversities are being used for estimating the directions of reflectors. However, during the transmission interval of the time division multiplex transmitters, reflected waveforms also experience Doppler phase shift in moving scenes, which is entangled with the phase variation of the antenna spatial diversities. As a result, moving objects can be smeared and appear in different locations than where they really are, and the resulting heat maps are severely distorted. To resolve the Doppler phase entanglement, we exploit redundancies in the virtual antenna array. That is, there are 32 pairs of co-located virtual antennas, for which the phase shift contributions from the transmitter and the receiver spatial diversities cancel out with each other, and the only phase difference between co-located virtual antennas is the Doppler phase shift, which we can directly measure and then compensate for throughout the remaining antenna array. Using this Doppler phase compensation algorithm, we can significantly alleviate the distortions, but it has some limitations. And so further correct for the residual distortions, we leverage the following insight. Although heat maps generated using a single transmitter have lower resolution and artifacts, they do not suffer from the Doppler phase entanglement. Therefore, we design our object detection neural network to jointly leverage the high and the low resolution radar heat maps to achieve accurate detection. The second challenge of cascaded MIMO radar is the ambiguity in Doppler velocity estimation, because Doppler phase shift wrap around over adjacent frames. Compared to single-chip radars, the frame rate of cascaded MIMO radar is 4 times slower, so the maximum unambiguous velocity is also 4 times lower. In order to reduce the Doppler ambiguity, we try to leverage all the transmitted chirps for Doppler processing, so the sampling interval for Doppler processing becomes 12 times shorter, and the maximum unambiguous velocity also becomes 12 times higher. We do so by canceling the transmitter antenna spatial diversities across different antennas. We adapt faster RCN framework in Radatron Plus network architecture, but we design the backbone network to have a two-stream architecture, which takes as input both high and the low resolution versions of the radar heat maps. We fuse the low and high resolution feature maps in the middle of the backbone network. Unlike prior work that directly fit the sparse 3D heat map into a 3D backbone network, we first take an arcmax operation along Doppler dimension to obtain a 2D Doppler feature map, where the pixel values represent the dominant velocity for each range Atomos pixel. We concatenate the Doppler feature map as a second channel to the low-resolution heat map input because they have the same dimension and resolution. Next, I will show a demo video demonstrating the performance of Radatron Plus on our urban street dataset. We show per-frame detection results without any temporal post-processing. The field of view is up to 25 meters, so further away objects will not appear. As you can see, Radatron Plus is able to accurately detect vehicles on the road, even in complex scenarios with multiple cars around. It can correctly capture the changes in orientation as the cars are turning in an intersection, which is the bottleneck when using low-resolution radars. Finally, it can also accurately detect vehicles moving towards the radar, even though the relative velocity leads to severe Doppler phase entanglement. For more details, please refer to our paper. The Radatron dataset is also available on our website. Thank you for watching the video.